Welcome to the Deep Dive, where we really try to get straight to the insights you need. Today we're looking beyond the flashy headlines about AI.
Yeah, we're diving into something maybe less glamorous, but honestly, super important. Industrial automation.
Exactly. Think about those jobs, the really monotonous, detail-heavy ones. They seem ripe for a smart shortcut. And that's where large language models, LLMs, might come in.
And that brings us to today's topic, a really interesting new benchmark called DrafterBench.
DrafterBench. Okay, so this isn't just general AI testing.
No, not at all. It's designed very specifically. It's a tough test for LLMs in civil engineering automation, particularly for revising technical drawings, which sounds simple, but is actually quite complex.
Right. So our mission today is to unpack why this DrafterBench thing is so needed. What are the specific hurdles LLMs face in this kind of industrial setting?
And we'll look at what the creators Yinqing Li, Zhendong, and Yishao actually found when they tested some major LLMs. There were some pretty surprising results.
Okay, definitely sounds like some aha moments are coming. So let's start there. LLMs are great at planning, writing code, solving problems.
Yeah.
Why the need for a special benchmark just for civil engineering drawings? What's so different?
Well, it's fascinating because these industrial tasks, like revising drawings, they have these really unique, very strict requirements, things that, most general AI tests just don't cover.
Strict how?
We're not just looking for a plausible answer like in creative writing. Here, you need absolute, rock-solid precision and reliability. One tiny mistake can be a huge deal.
Okay, so perfection is the goal, not just good enough.
Yeah.
That sounds like a massive challenge for current AI.
It really is. And one key thing the researchers flagged is this idea of implicit policies and prior knowledge.
Implicit policies, like unwritten rules.
Exactly. Think about a human drafter. They use common sense, they follow company norms, how to name files, how to save revisions, the best way to order steps, stuff that's almost never written down in the actual instruction.
Right, it's just assumed knowledge.
But LLMs, they often lack that common sense. You have to spell out everything. A person just knows to save the file as a new version, right? An LLM might just make the change and stop, which could be disastrous.
That's a really crucial difference.
Yeah.
It's like knowing the unspoken rules of the workplace. And I guess that ties into high robustness, too.
Absolutely. These tasks demand the exact same outcome every single time, even if different people phrase the instructions slightly differently.
So no room for creative interpretation.
None. Any variation, even a small one, could mess things up badly. Consistency is king here.
And obviously the accuracy of every detail must be non-negotiable. Missing one tiny step
Means the whole task fails. Forget to save. Task failed. Delete the wrong lines because the instruction wasn't precise enough for the LLM. Failed. Use the wrong parameter, even slightly. Failed. It's very much all or nothing. The stakes are just way higher than, say, getting a blog post slightly wrong.
Okay, so precision, robustness. Got it. But you mentioned another tricky part in just evaluating them. This what can be seen is not what has been done idea. What's that about?
Ah, yes. This is a really subtle but critical point for evaluation. You can't just look at the final drawing and say, yep, looks right.
Why not, if it looks the same?
Because an LLM might get to that correct final look using a really messy, inefficient, or even flawed process internally. Like maybe it created extra hidden objects or took 10 unnecessary steps.
I see. So the final picture looks okay, but the underlying code or structure is a mess.
Precisely. It might look visually identical to a cleanly done job, but that unclean solution could cause problems later, bigger files, harder future edits, maybe even hidden errors, so you need to look deeper than the surface.
Okay, that makes total sense. So to tackle all these issues, the implicit knowledge, the need for robustness, the evaluation problem the researchers built DrafterBench, how did they actually construct it to simulate a drafter's job?
Well, connecting it back, DrafterBench is really designed to mimic that real-world workflow. Its whole point is evaluating LLMs as potential automation agents for those sometimes tedious but vital drawing revision tasks.
And where did the tasks themselves come from? Were they based on real work?
Yes, very much so. For the task derivation, they analyzed over 100 real drawing revision files from actual design firms and construction companies. So it's grounded in reality.
That's important.
Definitely. And from that analysis, they identified 12 main types of tasks. These cover 4 kinds of operations like adding things, modifying content, mapping info, updating formats, and they apply across 3 main object types: text, tables, and those vector lines and shapes.
And these LLMs need specific tools, right? They could just think the changes onto the drawing.
Exactly. The benchmark comes with 46 custom tools built specifically for editing PDF drawings. These use libraries like Pima PDF, Report Lab, CV2, basically a digital toolkit for the LLM.
Like specialized software for the AI.
Pretty much. And the scale is impressive, too. It's got 1920 tasks in total, all checked by humans, and they even varied the quality of the instructions to mimic real life.
1920 tasks. Wow. And how does the LLM actually do the task in this setup? Does a human help?
Nope. No human in the loop during the task itself. The LLM agent gets the instructions, gets the files, and then it has to figure out the solution and write the code to call the right functions all in one go. It's fully autonomous execution.
Okay, here's the job figured out. But what about that evaluation problem? How did they solve the what you see isn't what was done issue?
That's where the really clever key innovation dual functions comes into play.
With functions.
Yeah. So instead of having the LLM directly modify the drawing for the evaluation run, they use these special functions. These functions don't actually change the drawing file. What they do is record the exact details of the arguments the LLM tried to use and the sequence of operations it planned.
So it's like a log file of the LLM's intentions.
Exactly. It allows them to compare the LLM's intended actions step by step against the correct ground truth actions. This gives a stable, accurate evaluation that isn't fooled by different coding styles producing the same visual output. It really focuses on the decision-making process.
That is very clever. It bypasses the visual ambiguity. So what specific skills are they testing with this setup?
They're focusing on 4 core capabilities: understanding structured data, executing functions correctly, following instructions precisely, and crucially, critical reasoning. These are really the bedrock skills needed for this kind of automation.
Okay, now this gets really interesting for me. DrafterBench doesn't just throw tasks at the AI. It actually controls the difficulty.
Yeah.
How did they do that? What knobs did they turn to really probe the LLM?
Well, this is where the granularity comes in. Quantifying difficulty for an AI isn't simple, right? So they designed 6 specific parameters grouped into 4 dimensions to vary the complexity.
6 parameters. Okay, break those down for us.
First, difficulty in understanding structured data. They varied the language style of the instructions. Sometimes it was structured, clear, short sentences. Other times, unstructured, long paragraphs, lots of extra information.
Like digging through a messy email to find the actual request.
Exactly. Can the LM find the signal in the noise? Second, difficulty in function execution. This was about the complexity of the required function calls. Simple tasks might just need 1 or 2 function calls in a line. Harder ones might need a complex sequence, like a branching workflow.
Right, a simple text edit versus, restructuring a whole complex diagram.
Then there's difficulty of instruction following. This had 2 parts: the number of objects the instruction referred to one thing versus many things, and the number of revisions needed one change versus multiple changes within a single instruction.
So basically, how much juggling does the LLM have to do at once?
You got it. More objects or more operations mean a longer, more complex chain of actions the LLM needs to plan and execute correctly.
And the last one, difficulty of critical reasoning. Sounds like where the real-world messiness comes in. Human instructions aren't always perfect.
Definitely not. This is key. It included 2 scenarios. One was vaguely defined values, like the instruction says, move the table to the left a little.
A little. How does an AI handle that?
Well, it shouldn't just guess wildly or ask back. The ideal agent needs to, as they put it, think carefully and self-correct, infer a reasonable standard value based on context, not just type a little into the parameter field.
Okay, so some basic inferences needed. What was the other critical reasoning challenge?
Incomplete instructions. For example, add the missing dimension, but it doesn't say what dimension or its value.
What should it do then? Just make something up?
No, that could be terrible. The ideal behavior, according to the benchmark design, is for the agent to log this issue, basically, flag it for a human rather than guessing and potentially adding wrong information to the drawing. It's about knowing its limits and following protocol.
Knowing when not to act is just as important. Okay, these parameters really give a detailed picture. So the big question, what happened when they ran the top LLMs, OpenAI, Anthropic, DeepSeek, Qwen, Meta models through this DrafterBench gauntlet? What did they actually find?
Well, the results were quite revealing. Looking at the overall performance, OpenAI's O1 model came out on top pretty consistently across most tasks. It showed, clear dominance.
No huge surprise there, maybe.
Right. Claude 3.5 Sonnet and DeepSeek V3 685B were pretty much tied for second place. But here's the kicker. Even the leader, OpenAI O1, it still struggled. It failed to get about 20% of the possible points.
20%. On tasks described as simple, monotonous, low-tech.
Exactly. It really underscores why this kind of focused industrial benchmark is so necessary. Even the best general models aren't quite ready for prime time in these very precise high-stakes roles without more work.
Wow, that 20% gap is significant. What about robustness? How do they handle the different difficulty levels?
Okay, digging into the robustness insights. For language style structured versus unstructured text, most models were actually quite stable. Performance only dropped by about 1%.
So they can mostly handle messy instructions.
Mostly, yeah. Claude 3.5 Sonnet showed a slightly bigger drop, about 5%, but generally that wasn't the main issue. Now, function execution robustness, handling complex versus simple function pipelines, that was tougher.
Okay.
There was about a 9% performance drop across the board when things got complex. OpenAI O1 was the most stable here, only dropping 7%, while Claude 3.5 dropped the most, about 11%. Interestingly, they often did best on tasks with fewer arguments or simpler steps.
Makes sense. Fewer chances to mess up. What about following instructions with multiple parts, multiple objects or operations?
For instruction following robustness, they did pretty well handling multiple objects, less than a 4% performance drop compared to single objects. And for handling multiple operations within one instruction, OpenAI 1 and Claude 3.5 Sonnet were again very stable, less than 1% drop. The others jumped around 6%. So following complex sequences seemed okay for the top models.
It sounds like basic execution and understanding messy language isn't the core problem then. Where did they really fall down?
It was the critical reasoning. That was clearly the major hurdle for all of them.
The vague instructions and missing info.
Precisely. When details were vague, like move a little, performance dropped significantly 5% for Quen, up to 12% for others. And when instructions were incomplete, performance tanked by about 18% for most models.
18% drop just because information was missing. Ouch.
Big time. Though, interestingly, OpenAI O1 showed much better resilience here compared to the others. It seemed better at navigating those ambiguities or incompleteness, relatively speaking.
Which leads us to that 20% gap you mentioned in the error analysis.
Yeah.
Can you elaborate on that? It sounds like a really key finding about where LLMs currently stand.
Yeah, this 20% gap is, I think, really insightful. It's not just about the overall score. It highlights a consistent pattern across all the models, even OpenAI O1.
What's the pattern?
There's a persistent gap, around 20 percentage points, between how accurately they perform individual subtasks, like figuring out the right arguments for a function or selecting the correct tool, and how accurately they execute the entire plan from start to finish.
So they're okay at the individual steps, but stringing them all together perfectly is the problem.
That's exactly it. They can understand a lot of the objectives, they can often pick the right tool for a single step, but they struggle to maintain that accuracy flawlessly throughout the whole complex sequence required to modify an object completely.
They drop the ball somewhere along the way.
Right. They're good at the parts, but perfecting the whole dance end-to-end without any mistakes, that's where they consistently fall short by about 20%. And in engineering, that lack of end-to-end perfection is, well, it's a big issue.
A very big issue. Okay, so putting this all together, what does it mean for the future of LLMs in places like civil engineering or other industrial automation? What are the main takeaways or directions for improvement DrafterBench points to?
Well, it definitely highlights the gap we still need to bridge between general AI smarts and the meticulous demands of industry. The study points to several key areas needing development.
Like what?
First, moving beyond instantaneous interaction. Right now, LLMs often default to, I should ask the user, or just putting in a placeholder if info is missing.
Right, they want clarification.
But in many industrial workflows, like this drawing revision task, the goal is no human involvement during the process, or maybe only indirect interaction through logs or reports after the fact. LLMs need to learn to follow specified policies like log incomplete instructions, don't ask, rather than always defaulting to immediate interaction.
They need to be more autonomous and follow procedures, not just be conversational partners.
Exactly. Second, they need a deeper understanding of details. We saw they struggle with vague terms like a little. They often just fill in the vague description literally, instead of inferring a reasonable value. They need better reasoning, better speculation about the user's actual intent.
More common sense reasoning, basically.
Mm-hmm. And related to following procedures, there's the implementation of new policies.
What do you mean, like company-specific rules?
Yeah. The study noted LLMs can be kind of stubborn. If a new company policy conflicts with their ingrained training or default habits, they might resist implementing it. While that resistance can be good for safety sometimes, for more routine stylistic policies, they need to be more adaptable, more tolerant of implementing new rules to fit diverse industrial needs.
More flexible to custom workflows. Makes sense. Any other big areas?
And finally, just the need for a broader scope for benchmarking. DrafterBench is great, but it's English only right now and focused just on this one task in civil engineering. Future work needs to expand multilingual inputs, different types of industrial tasks, maybe manufacturing, logistics, quality control, to really test and improve the general applicability of LLMs in industry.
So, wrapping up our deep dive into DrafterBench, it really paints a picture, doesn't it? LLMs are incredibly powerful, yes, but putting them into these high-stakes, super detailed industrial roles, it's a whole different ballgame.
It really is. It's not about just getting an answer. It demands perfect, robust, policy-driven execution end-to-end.
And that persistent 20% gap in getting the whole plan right, even for the best models, that really tells you where the current frontier is.
It shows the challenge ahead in moving from generally capable AI to truly reliable industrial automation agents.
So here's something to think about based on all this. Given these findings, especially that 20% gap in execution accuracy, what other industrial jobs ones we maybe think of as too human or needing too much careful detail might actually be candidates for LLM automation if we acknowledge these limitations and perhaps design workflows around them? What stands out to you about this tension between an LLM's amazing general abilities and the very specific, structured, almost unforgiving demands of an industry like engineering?